11:50 today. I can't really stay beyond because this time around we've got that job candidate, and so I've got something to go to like right away. So this will be a relatively short class as a result.
All right.
Where we are in the class right now, let me share screen. There's James. Great. Hey, James.
There you go. Hey.
Sorry if there was some confusion. Nathan was emailing me saying he was not sure whether we had class or not today.
Uh,
So I guess I was not clear last time. Um, where we are right now in the notes is this. We are starting lecture set 2, part 2, which corresponds to this part of our book. We're to McIntyre sections, basically 6.2 to 6.3. Okay, this is basically wave packets and uncertainty. So this answers the question that Nathan asked last time, a very valid question, which is, where are we in the book right now? So this is where we are. We're starting here. And let me see here. Got some figures that I kind of want to pull up from the book. I can sketch some of these. Some of these I'm going to pull up. Okay, so as a simple preliminary example or paradigm, with no pun intended, as a reference to this textbook, um, let's consider a discrete superposition consisting of 3 pulses. So consider 3-pulse discrete. It's not how you spell that word. Superposition. Okay. Um, so basically 3 eigenstates added together. Okay. Basically, the states that we're going to do is one of them will just be P equals P naught. One of them is P equals P naught minus delta P, and one of them can be P is P naught plus delta P. All right. So for convenience, this is sort of the central mode or peak mode. These two are side modes or side peaks. All right, so basically this superposition would look something like this. You have psi p of p naught is going to be 2 of psi p of p naught minus delta p is equal to 2 of psi p p naught plus delta p. In other words, central mode has 2 times amplitude of either side peak. or side mode. McIntyre plots this for you. I don't really want to mess with trying to find where on this computer I put said plot. Basically, you could think of this as here's psi sub p of p, and here's p. These are your two axes. And the plot, basically, you have one here. You have one here that's twice as tall. And then you have one here that's again the same height as the original. And so these would represent P naught, P naught plus delta P, and P naught minus delta P. In some sense, this is a very loose approximation of some distribution. Might be, for example, the Gaussian distribution. Oops. What? And so it's like we've kind of, in some sense, picked like the center of the Gaussian distribution and say like the full width half max, or maybe even the 1 over E points, the waste, if you will, from this Gaussian distribution. Okay. And right now we're just trying to build for ourselves a very simple model. What do we expect if we're going to add these things together? Oh, our first guest. Hello, Colin. Glad to
Hello.
have you. Glad to have you. We're just starting. We got a little bit of a late start because there was some confusion about the start time. So we're looking in sections 6.2 and 6.3 of the book. And I'm just sketching the superposition that we want to look at for our free particle. Right now, we just want a discrete superposition. Later, we'll do a more continuous one. Okay. So in some sense, what's going on here is you're getting a distribution or a superposition that you expect to look kind of like this as a sketch. You have one that has an amplitude like this. So this is like my P naught. And then I'm adding to that two side peaks, one of which is sort of a lower amplitude and maybe a higher frequency. So this is dang hard for me to draw on here. Something like this, I guess. And then to that we're adding, and I'm sorry, this is not going to be to scale, something that is maybe more akin to this. And what we expect to get when we add these together is some sort of a pulse train that maybe looks like this. Maybe we get like that, and then another one of these guys. Okay. And I can do better than just this sketch because I took some time to go to what everybody here knows as my favorite program for doing this kind of crap in. I opened up Octave and I made for myself a code that I could try plotting these in. So a little walkthrough of what this code is that we're looking at. I need to change this to n equals 1. If I leave it at n equals 0 and I tell it to plot, then I get something that looks like this. Don't worry about the fact that there's no labels on the axes, anything like that. This is just kind of for show. This is obviously just a sine wave with a whole lot of oscillations worth of the sine wave. Now, why did I allow so many oscillations? Because for the choice of the parameters that I've made here, if I change this to n equals 1, this basically means we're adding in one pair of side peaks. So this is how many side peaks do we want to add to this initial function? And basically, I have a reduction factor in place. So each time I add another set of side peaks, it's like half as big as the previous set. So for n equals 1, we're basically plotting the scenario that I've outlined here. So let's go ahead and plot what that actually looks like. There you have it. Okay. And in this case, I happen to choose a delta P that's 1/10 as large as my P naught. So, I can get a few side peaks before I start running into some problems there. But this right here is the pulse type you get. And, we can change stuff like maybe I decide that my delta P doesn't need to be 1/10. Maybe I decide it needs to be a fifth. And if I replot it, I get a slightly different shape. If I decide to make it a hundredth, slightly wider pulse, etc. Okay, so the larger my delta P is here, the narrower my pulse, my individual pulses on this pulse train become. Okay, so let's keep some of that in mind as we go through this derivation. So what is it that I'm basically doing to write that code? What is the basic um, math behind it? Well, first of all, we're just looking for what's the total um, psi at time 0 as a function of x. And the answer is it should be the sum of all of the individual sine waves that I've put in, all the individual eigenstates with their respective amplitudes and the respective eigenstates in X representation. Okay. And recall from last time, the discussion of Fourier transforms, that this guy right here, this eigenstate, is given in terms of um, our momenta as 1 over root 2 pi h bar e to the I pjx over h bar. Okay, so these are these individual eigenstates. We've set some amplitude conditions such that basically Cj, we could say like C, I guess we could call them 1, 2, and 3, or we could call them -1, 0, and 1. So C -1 equals C1 equals 1/2 of C0 in those terms. That was our amplitude conditions that we've set up here. Okay, so that basically means that we expect this guy, psi of x comma 0, to look like 1 over square root 2 pi h bar. And then first term is 1/2 e to the I, and now we have to put in our momentum. And so our first state's momentum, this is sort of like the first state or the minus state or whatever you want to call it within the superposition. So this is P naught minus delta P. x over h bar. Second one is just 1 of e to the I p naught x over h bar. And then the last state, again, amplitude is a half e to the I p naught plus delta p x over h bar. Okay, so here's our sum. Now, we now want to say, okay, let's get the wave function to represent this wave packet. And to do that, what we're going to do is follow the Schrodinger time evolution recipe. So we basically want to see, what is this wave packet doing in time? And the answer should be, if we want to go from psi of x comma 0 to psi of x comma t, use the Schrodinger approach, which is that this should look like, again, summing over the j's, c sub j by p sub j of x, and then this phase dependent term, e to the minus I ej t over h bar. Okay, and oops, and we may say, okay, so we know what this is, we know what this is, we know the t and the h bar. What is this energy term right here? And the answer is, remember that this is an unbound state, or these are supposed to be unbound states. So from the Hamiltonian, we know that this right here, E sub j, should look like P sub j squared over 2m. Okay, because again, it's unbound. Oops, I'm writing U for potential energy. I'm still in physics 1 and 2 mode. V is 0. Potential energy is 0 here. Okay, so basically what this means is, in terms of our states, we would have state 1, which is the minus state, is P naught minus dp over 2m. This is squared. E0 is just P naught squared over 2m. And E for the plus 1 state becomes P naught plus delta P squared over 2m. Okay. So these two, if we expand them out, would be P naught squared plus or minus 2 P naught delta P plus delta P squared over 2m, for what it's worth. Okay. Now we need to make an assumption. So those plots that I showed you a little earlier on here, you'll notice that I kept the delta F, which is again equivalent to our delta P's here. I kept those deltas smaller than F naught. F naught, or P naught by extension, is relatively valued at 1 in this code. These are 0.1 or 0.01 or even like 0.2. So notice that the basic thing that I applied there was, what if delta P is many times smaller than P naught? So factor of 10, let's say, maybe a factor of 5 is doable. Factor of 10 better, factor of 100 fine. Okay, so if that's the case, then for our purposes, this delta P squared term might as well be treated as a 0. All right. And so with that in mind, this becomes p naught squared plus or minus 2 p naught delta p over 2m. Okay. So now let's go back to our states and plug this in. Whoops. Let's plug this in and get our states written out as functions in time. When we plug those in, we have 1 over root of 2 pi h bar. And this is times 1/2. And then you have your e to the I. Whoops, I want some parentheses here. E to the I p naught minus delta p times x over h bar. And now I have my time dependent term up here, which is negative I p naught squared minus 2 p naught delta p times time. And then you have your over 2m and over your h bar. Okay. To that we add 1 of e to the I p naught x over h bar and e to the minus I p naught squared t over 2m h bar. And then the last term is our 1/2. And now it's basically these two terms, but with pluses in them in this part. So you have I p naught plus delta p x over h bar and e to the I p naught squared plus 2 p naught delta p t over 2m h bar. Phew. That's a mouthful to say. It's a lot to write. Essentially, you now make a series of simplifications. For example, let's look at this term here and this term here. We'll ignore this middle term. These two terms, you have effectively an e to the minus I, e to the minus I times something like dp x over h bar minus p naught dp t over 2m h bar. And this term right here, and again, there's a half in front. This term right here, if we combine these guys, you end up with e to the I, and then it's actually the same thing, dpx over h bar minus e naught dpt over 2m h bar, both of which are then also multiplied by this leading I p naught x over h bar term. Okay, so in some sense, like, all right, you also have an e to the I p naught x over h bar, and over here you have an e to the I p naught x over h bar. But the key thing is that you have this and you have this. And so if we let some dummy variable be given by basically this difference, dpx over h bar minus p naught dpt over 2m h bar, then these look suspiciously like a 1/2 of e to the I p naught x over h bar times e to the minus the dummy variable plus e to the plus of the same dummy variable. All right. And so now we say, all right, do we remember what the identity is that goes with this? And the answer is, I hope you do know what this is, because this looks like a cosine. Well, it looks like 2 of a cosine, because remember that sorry, I left off an I on both of these. E to the I would be cosine of this thing plus I sine of this thing. And e to the minus I times the same is cosine of the negative, but cosine's even, so you just leave with a cosine. And then I sine of the negative, but sine is an odd function, so you just get minus I sine of the same. And so if we're adding these two things together, you're just left with 2 cosine of the thing. Okay, so now coming back here, we say, all right, what does that mean we've got? Well, it means that we've got psi of x comma t is equal to, you still have this term in here, but this term is e to the I p naught x over h bar times e to the minus I p naught squared t over 2m h bar, plus, given that there's a 2 here and a half here, those would cancel, and I'm left with e to the I p naught x over h bar cosine of phi. And so now I can basically take this right here, throw it back in here, and then make sure I haven't messed anything up. Yeah, okay, this is fine. So throw this back in here into the cosine. Basically divide out this from both sides, and you get your final expression, which is like this: e to the I p naught x over h bar minus p naught over 2m h bar t divided by, remember that we had that amplitude out front, the root 2 pi h bar. And then what's left inside is 1 plus cosine of our dummy variable, which, remembering what our dummy variable was, is dp over h bar. And we could basically divide that out from the x term and the p naught over mt term. All right. And so now we say, this is a sort of final-ish form, so you could box it if you want. Awfully big equation to box, but here we go. And now we say, okay, wait a minute. This is a cosine. We expect this thing to be some sort of a traveling wave. Remember that a basic waveform, like wave on a string traveling wave, has the form y is y max or amplitude times, and you can use a cosine or a sine, cosine of kx minus omega t. But if you do omega over k, you get the speed. And so this right here has the form y max cosine of k x minus v times t. All right. And so now we look at all the stuff that's in this and we say, if this is the form that this thing is taking, that means that this right here must be my k because it's occupying the k location. This right here must be my v. Okay, so k is dp over h bar. V is p naught over m. Okay, some comments. So our waveform for psi of x comma t contains the expected form that it should be some function of x plus or minus a speed times time. And in fact, it kind of contains it twice, but each time with a slightly different argument. And those arguments kind of end up, where's the other time? Right here. This is k. And this right here now is 2v. Okay. So we have our phase velocity, we have our group velocity. So remember that this right here is sinusoidal fundamentally. This is our phase term. This right here, sinusoidal, this is your group term. Your phase term has v phase. We're looking at this port right now. P naught over 2m. I accidentally circled the h bar. P naught over 2m. Your phase velocity. This right here that came out of this is your group velocity. And this phase term, or this part of it, if you will, is kind of the carrier in some sense. So this is your carrier wave. Notice that your carrier wave, K, is in fact, K is in fact P naught over H bar. In other words, your wavelength for your carrier is set by that central node. Your phase speed set by this speed for your central node, and it's half of the group speed. Okay, that was as discussed last time. So now we've kind of derived it explicitly. This part right here, this is your actual wave packet. And so this right here, these are the group terms.
Dr. Sanders.
Yeah,
For the phase velocity, is that supposed to be p naught squared?
up here.
Yeah.
No,
Okay.
no, it's not.
Thought it-
We did some division, like there's some algebra steps from getting where we were here with division to getting the final form here that I kind of cut for brevity. But if you go back and like work through all the algebra to it, you'll find that no, in fact, this does work out to just P times T over 2M.
Okay.
Essentially what's happened is we've divided out somewhere an additional P naught from everything. And so that ended up kind of getting removed from all of this stuff. But good question, because yes, originally these were P squareds from the energy. but this part right here is the part that's going into the phase. I accidentally circled the H bar as well. So these right here are your phase terms. And that's telling us what does the carrier wave do. It's a kind of analogous to if I pull this thing up, each of these packets here might be moving from left to right, and they have a particular speed at which this packet as a whole is moving, and that's these terms here. But within that packet, this frequency will also be moving relative to that packet. In fact, it's moving slow relative to the packet. It's still moving left to right, but it's moving slower than the packet is here. And this speed, this phase speed, is telling us what that is doing. This K, remember K gives you wavelength. This is giving us the distance from this point to this point. This one right here would be giving us distance from this peak to this peak. So if I slot this in here and label those explicitly for you all, whoops. You have to do a little bit of cropping. Maybe a little bit of stretching out as well. Nice big image. So here's what my group terms are doing. So this is sort of like the one pulse to the next pulse. So this would be lambda group. Okay, and then this thing itself is moving at V group. And then down below, we have a peak to peak distance like this. This would be V phase. And these individually are moving this way. Sorry, this is lambda phase. Lambda phase. And these right here individually are moving at V phase. And looking at the forms we have here, V phase in this case is less than V group. And that kind of is obvious from the P naught, M, M. Now we look at the Ks. This is P naught over H bar. This is dP over H bar. dP is supposed to be much less than P naught. So that means that K group, this is the group, K group should be less than K phase. But remember that these are just 2 pi over lambda. So that means lambda group is greater than lambda phase. And so we come back over here and say, is that consistent with what our picture shows? And the answer is yes. Okay. What else? Do I have other notes I want to say? Yeah, I got a few other notes. Okay, so book actually does 2 plots in here beyond like what I've done here. And then it suggests homework problem 6.8 to animate these plots via computer. And you could basically write something like what I did in this octave code. You just have to now include some time. So again, here's my octave code for this. Again, for me, F and P are equivalent because of the way that I've written this code. A represents the amplitude is sort of like those C terms in, in this sum right here. So you can do something similar if you'd like. I don't, let's see, do I have I don't really have a time in the sense that I already did this as if it was frequency and time rather than position and momentum. But in principle, you could add another step in here that lets everything move in time and you could see them all moving. That may be an interesting project for one of you guys to do. Might even, if it's a good drawn out project, be a good one if somebody's thinking ahead towards what are we doing for presentations. Okay. Um, Note that the group velocity over here, getting a little cluttered, I'll rewrite it over here. Note that my group velocity V group was P naught over M. Note that my phase velocity was was P naught over 2M. But this right here corresponds to classical particle velocity. So my group velocity corresponds to my classical particle velocity. Okay, another note for a particle of momentum P naught and mass M, of course. Another note, the discrete superposition is creating a series of wave packets. So it can't really adequately represent the localization of a single particle. You'd need to have a more continuous superposition to do this. And then last but not least, since we have an infinite series of these, it's not really normalizable. So we can't quite use it to do probability or expectation values. And again, for that, we would need to go to continuous. So on that note, I'm going to have to stop class, but that is a good stopping point. I have to stop class because we have this job candidate here and it's basically like time for me to go meet with him. So we'll quit the recording.